Kepler's laws of planetary motion. So Kepler made some laws regarding the motion of the planets, and a little bit of history. There was a person by the name of Tycho Brahe, and he worked in an observatory, and he collected very accurate and detailed data on the positions of the planets over a large number of years. Then Tycho joined him as an assistant, and soon thereafter, a year or two later, Tycho Brahe died, and Kepler had access to all of his data. And then he worked with that data for many years, and ultimately found some relationship between the motions of the planets, which are known as Kepler's laws of planetary motion. So the first law of planetary motion is that the planets move in elliptic orbits. Around the sun. Okay, and that was something that was not very well accepted, because people thought that the planets, it was now accepted that the planets move around the sun, so it was bad enough that the Earth was not in the center of the universe, and now we know that the planets were not even going in circles but in ellipses. So an ellipse is sort of a distorted circle, and they thought that the heavens have to be perfect, and a circle is a perfect figure. But his data showed very clearly that the planets moved in elliptic orbits. Now an ellipse is a figure which is like an oval, is slightly extended, and there would be two centers or two focuses or foci. So this would be the two focuses, so one focus here and one focus here, and there would be a major axis, and this would be the minor axis, and the bigger the difference in these, the more eccentric it becomes. So the eccentricity of a circle is is 0. The eccentricity of a circle is 0, and the two foci just meet at the same point. Now, so he said that the sun is at one of the focuses. That would be the sun. The other focus is blank, there's nothing there, and the planet would be going around it in an ellipse. So that's the first law. The second law says that as the planet is going in this elliptic orbit, so let's make it again, and somewhat more eccentricity, even though the planets mostly are not in such an eccentric orbit. Let's say that's one of the focuses, the other one is irrelevant. Let's say the planet is at this position at any time t equal to 0. The planet is here, and then we select any duration, let's say 1 day or 1 month or a week or so on. So let's say we select a time t when the planet is here, call it t1. Then if we join this line, this is the line joining the sun to the planet, and as the planet moves here, this line will also move along with it like this, and it will be here. So it will sweep out this much area in time t. So the line from the surface from the sun to the Earth or any other planet sweeps out so much area in time t. Now if we consider, not here, but let's say t equals 0 is here, and we take the same amount of time, so let's say we took it as 1 week, how much is the area swept out by this line in a week? So if we do the same thing in a week over here, so this is again the same distance in time, and again we have this line joining here, and this is the area that this line, this radius sweeps. So Kepler's law says that the area swept by this radius is the same in same length of time. So because this is longer and this is shorter, so it means that the planet has to be going slower here and it has to be going faster over here. So it just shows that when you're further away from the sun, you're moving slower, and when you get close to the sun, you're going faster, because this radius vector sweeps out equal areas in equal times. So you select the same amount of time anywhere on the path, and this would have the same amount of, the area would be the same. So that's a second law. The third law states that if we can do it here, if this is, say, t equal to 0, and let's say this is some position where we say t equal to 0, and the planet goes around the orbit and reaches back at the same place at time t equals some t, this t would be the period of orbit, or the orbital period. That's the time taken to complete one revolution, or we can say it's 1 year for that planet. Okay, the year we use for the Earth, but if you have Mars, well, 1 year for Mars would be much longer, and that's the time it takes to make a complete orbit. So that's the time period. And well, the distance is, this is the shortest distance, this would be the longest distance, but if we take an average distance and we write it as a, as an average distance from the sun to the planet, then he said that t squared is proportional to a cubed. So a is the average distance to the planet. When the distance increases, so you have a planet that's at a much bigger radius, so a is bigger, then a cubed is proportional to t squared. And this can also be written as t squared is equal to some constant times a cubed. Now we can solve a little, do a little math to find or even prove this equation, which we can do pretty easily nowadays, now that we know the answer. So let's assume that you have the sun over here and you have a planet here that's going in an orbit, and at this it's moving in this direction, and this is the mass of the sun, that's the mass of the planet, and the distance between them is r. Then the planet is being pulled towards the sun by a gravitational force, so Fg is g, mass of the sun, mass of the planet, over r squared. That's the force at which it's being pulled inside. And because it's going in a like a circular, a sort of a circular orbit, it has a centripetal acceleration and a centripetal force, and that centripetal force is provided by gravity. Okay, there's no string. If you do this with a stone and a tied to a string going around in a circle, the tension in the string provides a centripetal force. Here gravity provides a centripetal force, so this must be equal to the centripetal force, and the centripetal force is the mass of the planet, speed of the planet square over r, mv squared by r. So this is the speed of the planet. Now if you equate these two, so g, mass of the sun, mass of the planet, over r squared equals mass of the planet, speed of the planet square over r, we can cancel out the mass of the planet and one of these r's, and we can get Vp square is g, mass of the sun, over r, or we can simply get the speed of the planet is g, mass of the sun, over r square root. That gives us the speed with which the planet is going around the sun. And It can also give us the speed with which a satellite is going around the Earth if you put the mass of the Earth over here. Now, we can also say that the speed of the planet is the entire distance it covers divided by the time it takes to cover that distance. So it's a distance over time, and the distance is 2 pi r, and the time is capital T, which is 1 year, or the orbital period. And we can substitute that in here or here. So let's do it in here, which is the same equation. So we get 2 pi r over T, that becomes the V, and square it becomes G, mass of the sun, over R. And then we can get from here, we get 4 pi r square, 4 pi square r square over T square equals G ms over R. And we rearrange that, this becomes R cubed, that becomes T square. We get T square is 4 pi square r cubed over G, mass of the sun, and that becomes the equation that Kepler had, K a square. So this is the K for the sun, and R is the distance to the planet, the average distance to the planet. Now let's do an example, and in this case, instead of dealing with the planets and the sun, we can consider our space station, and Kepler's law would apply to it also. So here we have the Earth, and here we have the space station going around the Earth, and the question is, how long does it take to make a full circle? So what is the time period, the time it takes for the space station to make a full circle? T is what we're looking for, and well, the height is 350 kilometers, and so we need to add the radius of the Earth to it. And RE is 6371. Add them together, we get 6721 kilometers. That becomes R. And so we use it, our equation, T squared equals 4 pi square R cubed over G, and now we have the mass of the Earth and not the sun, because the Earth is the object around which it's going. We plug in these numbers, converting that to meters, plug it in here, solve it, and get the square root, and T comes out to 5485 seconds, which is 1 hour and about 31 minutes. So it takes 1 hour and 31 minutes to make a full circle. Well, we could also find the speed with which it's moving. What is the speed of this as it's going around? We can get it from 2 pi r over T, which we found here, or we can also use G, mass of the Earth, over R square root, and get the speed of the space station. Well, that's the speed that you would have to give it if you want it to stay in orbit. Now, one more thing, and this is the last thing that we'll do here, that if you have the Earth over here and the satellite is here, this is the space station, and it takes 1.5 hours to go around the Earth. If it's further away, if you increase the R, the time increases, so it's going to take longer to go around the Earth. So there will be a distance over here, some distance, in which it takes exactly 24 hours to go around the Earth. If that happens, well, the Earth is also taking 24 hours, and this is also taking 24 hours, and so we have a satellite that has a T equals 24 hours, is called a geosynchronous satellite. it's synchronized with the geo. Geo is the Earth. So it's synchronized with the Earth. The Earth's period is 24 hours, so its period is also 24 hours. Now, if the satellite, if this geosynchronous satellite is also above the equator, then it's called a geostationary satellite. And for people on the surface of the Earth, so if that's the equator, that's the North Pole, and the satellite is, that's the center of the Earth, the satellite is directly above this point, and it's taking 24 hours to make a full circle. Then when this point on the surface of the Earth reaches here, the satellite would have reached here, and when this point on the surface of the Earth on the equator reaches here, the satellite reaches here. So the satellite is, because it's taking 24 hours to go around the Earth, and the Earth is taking 24 hours to go around itself, and the satellite is also taking 24 hours to go around the Earth. So it's always above the same point. And such satellites are used for communication, and especially we have these this satellite TV. All these satellite TVs, their satellites are positioned right above the equator at a certain distance where the T is 24 hours, and they become geostationary. And that's why when you have a dish antenna, it always points in that direction. The satellite is always above that point. And how far is this satellite? Well, use this equation. Put 24 hours here after converting to seconds, 4 pi g, mass of the Earth here, and you can get the distance to that satellite from the center of the Earth. This would be from the center of the Earth. So subtract the radius of the Earth and you can get the height or distance from the surface of the Earth. Okay.